Welcome back to Interesting Questions. We got a good one today. It's on the Large Hadron Collider. It's a very interesting subject, science subject actually. One of my first videos on the Hadron Collider. I know there's a smaller one here in the U.S. That's why this one's called the Large Hadron Collider. But we actually have one here in the U.S. I think it's in Ohio. I could be wrong. You could fact check me and leave a comment if I am wrong. But I appreciate you guys joining me. Like I said, if you enjoy videos like this, you like videos like this, smash that like button. Share this with friends, family. If you find it intriguing, I mean, these are some intriguing subjects to me. That's why I enjoy bringing them to you. And subscribe. Hit the subscribe button, man. I need those subscriptions, so please subscribe up, and so I can make more content like this. But without further ado, let's go ahead and get to the video.
Planet. The Large Hadron Collider is installed underground near the French-Swiss border. It's a ring-shaped tunnel with a circumference of 27 kilometers or 16.7 miles. Two vacuum pipes are installed inside the tunnel, which intersect in some places. 1,232 main magnets are connected to the pipes. Their task is to accelerate protons to a speed close to the speed of light, and then hold this stream so that the particle beams don't crash into the wall. In order for the magnets to work, they're powered by superconductive cables with a total length of about 250,000 kilometers, or about 155,000 miles. If scientists got tired of the LHC and they decided to dismantle it, these wires could be wrapped around the Earth about 6 times at the equator. And even after that, there'd be enough wire left to run a power grid somewhere in Antarctica. Although, why a power grid in Antarctica? Well, they aren't planning to disassemble the LHC yet. However, it could be considered the largest refrigerator ever created. For proper operation, the collider magnets need to be cooled to minus 271.3 Celsius. That's minus 456.3 Fahrenheit. That is, to create.
Yeah, I believe, as he's probably going to say right now, is you have to cool it down to this temp to create a vacuum, to kind of replicate space. Like, space is freezing, so that's they have to kind of recreate that type of environment.
Create a temperature lower than in space. To get this cold, 120 tons of liquid helium is poured into the LHC. Now, look at the refrigerator in your home. In it, there are special substances, refrigerants, that create cold. Liquid helium is one of them. In one household refrigerator, there are approximately 30 to 50 grams, or 1.05 to 1.76 ounces of refrigerants. So, we can say that the LHC surpasses this indicator by approximately 4 million refrigerators. Only instead of cooling products, it helps solve the most complex problems of modern physics. For example, what does matter consist of? From school, we know that matter consists of molecules, molecules of atoms, and atoms of protons, electrons, and neutrons. But modern science has gone even further. It turns out that even the smallest particles of the atomic nucleus, for example protons, consist of even smaller particles, quarks. Want to know how small they are? Then imagine that an atom has grown to the size of the Earth. Then a proton would have a radius of about 100 meters, or 328 feet. That's almost the length of a football field. In this case, the quark would have a radius of about 5 centimeters, or 2 inches. That is, it could fit in your pocket. But how can we examine such small particles? This is why the LHC was created. You take two beams of protons, accelerate them in opposite directions, and collide them with each other. What would happen if you put a brick on the ground and threw another one on top of it? Most likely, small fragments would fly off in different directions. Similarly, when protons collide, tiny particles can break away from them. In ordinary language, a collider is needed in order to see what happens when the protons and heavy lead nuclei collide. As the creators of the project admitted, pushing two protons together is about as difficult as getting a needle into a needle, provided that the distance between them is 10 kilometers or 6.2 miles. And at the same time, they need to collide exactly in the middle. Not so easy. In addition, these small particles are invisible, so physicists can only study them by examining the tracks they leave in their wake. Another task of the LHC is to find something new. It was with its help that the Higgs boson was discovered. This invisible particle can be called the foundation of the universe. After all, it's this particle that gives the other ones, and therefore all matter, mass. It turns out that if it disappeared, all particles would become absolutely weightless and fly around the universe at the speed of light. In addition, with the help of the LHC, it's possible to study other elementary particles. Each of them helps in the emergence and interaction between atoms. And each of these particles is so small that they can be detected only when proton fluxes collide. Scientists register the particles that are then formed with the help of special detectors.
I guess that's why they refer to it as an atom smasher. I'm just curious, is that how are they breaking up atoms into these subatomic particles? I'm curious as the process of that to break up atoms into these tiny, little subatomic particles that go beyond a proton, an electron, and a neutron. It's kind of fascinating to me. But I guess that's what they were saying is that the Hadron Collider itself is literally like recreating the Big Bang. Because that's what they're saying. The Big Bang is believed that there was something like subatomic particles collided. What that did is that generates electricity. It's almost like, you rub your hands together, you create friction, you generate heat. The heat you're actually generating is energy. So this is one of the, the aspects behind this is that they're literally like colliding these particles and kind of creating these little small Big Bangs. And even in some ways I've heard even generating black holes with the amount of energy that it's minute, it's tiny, and it's also in a vacuum, it's in a containment. But they're getting data off this information on basically how the Big Bang occurred.
Another interesting area of research is antimatter. In our world, atomic nuclei have a positive electric charge. Negatively charged electrons revolve around them. But for each particle of an atom, you can create a double, an antiparticle. It has the same mass.
Yeah, it's like if you take a magnet, a plus and a minus, as it's showing right there in the imagery, a plus and a minus. When you try to push those magnets together, they don't want to come together. So this is how they're saying that, you have your nucleus and you have your protons and your electrons and neutrons. The more of them you have around an atom, the denser the matter becomes. So yeah, it's pretty interesting, But it's kind of weird too, like how they're using magnets in this project to kind of manipulate these particles. So they're probably utilizing magnets to withdraw these subatomic. They separate the protons, electrons, and neutrons. Then they separate the more minute subatomic particles from those protons, electrons, and neutrons.
Mass and properties, but the opposite charge. For example, an electron is negatively charged, and its antiparticle, positron, has the same mass but is positively charged. The same goes for protons. Protons are located in the nucleus of an atom and have a positive electric charge. But their antiparticles, antiprotons, carry a negative charge and at the same time have the same mass. We can say that antiparticles are a mirror image of ordinary particles. If you approach a mirror, you'll see your reflection in it. If you wave to it with your left hand, your mirror double will answer you with a wave of its right. Antimatter is similarly arranged. With the help of the LHC, it's possible to not only create antiparticles, they can also be combined with each other to create whole atoms of antimatter. Under ordinary conditions, when one proton and one electron are joined, a hydrogen atom appears. Now, we can take two antiparticles opposite to the proton and electron, the antiproton and positron.
Prime example, you have two of them, it creates hydrogen, which is H2. So water, H2, two hydrogen atoms, one oxygen atom makes a water molecule. Pretty interesting, huh?
Connecting them, we get an antihydrogen atom. It will have the same properties as hydrogen itself, but only when antihydrogen collides with an ordinary atom would an explosion occur. A strong explosion, as a result of which an incredible amount of energy would be released. 1 kilogram, or 2.2 pounds of antihydrogen, can produce slightly less energy than was released during the Tsar Bomba explosion. And that was the most powerful of all hydrogen bombs ever created by mankind. Most physicists believe the LHC is pretty cool. There's only one small problem. It's believed that one of its future experiments could destroy our planet, or at least it could create serious problems. In 2008, opponents of the collider, Walter Wagner and Louis Sancho, even went to court. They demanded a prohibition on starting up the LHC. The applicants feared that if protons collided so strongly, they could form a microscopic black hole. The gravity of this object would be so great that it would immediately begin attracting the surrounding molecules, or it might completely drag the entire Earth into it. But don't worry, none of the past experiments have confirmed the possibility of creating black holes. Even if such objects appeared inside the tunnel, their size would be so small that they would evaporate instantly.
You know, the physicist, Stephen Hawking, I think had issues with the Large Hadron Collider. And I think one of the issues he had with the Large Hadron Collider was that black holes. I think, though, that they have discovered in recent years, because Hawking he passed away some time ago, but he was kind of against them turning this thing on. He was one of the physicists that I guess kind of had issues with it. He also had issues with trying to communicate with extraterrestrials, which also made sense because he's like, how do you know that they're peaceful? What if they come here and they don't care about us? They just want resources. They'll decimate us because they're far more technologically advanced than we are, which that makes a lot of sense, you know. Yeah, I've heard that minute, tiny black holes, I think, have appeared, but there's not enough like energy sustainability or something. There's some issue where they appear, but here's another theory by Hawking's was when they're creating these environments, black holes can steal our memories. So one of the theories behind them creating these little, tiny subatomical black holes is that their energy is so powerful. They're saying this is what may be generating the Mandela effect, is that you're literally branching two parallel universes together, and then some information from one universe slides in, and then other information from another universe. The information is changing paths between these two parallel universes, and that's one of the theories behind the Mandela effect, is that's what's causing the Mandela effect, is because that information is affecting some of our alternate selves in another universe. So they're literally it's stealing our information, our memories, and it's literally transmitting it to our alternate self, you know, in this parallel universe. Then we're exchanging information with them. This is why we all have different memories of like Berenstain Bears or the Berenstein Bears, or I'm gonna do a video on the Mandela effect because it's also a very interesting subject. But this is one of the theories behind the Large Hadron Collider, is that it may be stealing memories from us and exchanging it, opening these tiny little portals to parallel universes, and like we're exchanging information with our alternate selves in these universes. We're exchanging information back and forth. It's a crazy concept, but I think string theory might back up some of these theories.
So the lawsuit to ban the LHC was rejected by the court. The LHC started up, and so far it's been working successfully. There's another potential threat. Scientists believe that in some places of the universe there are wormholes. These are hypothetical objects in which space-time is curved. We can say that these are tunnels connecting two remote areas of space-time. And if you enter one of these tunnels, you could either travel in time or instantly move somewhere very far away, even to another universe. Some scientists fear that high energies may create such a wormhole inside the LHC itself. However, this is just a theory. The creators of the LHC claim that such particle collisions occur on our planet even without human intervention. It's believed that for billions of years, various cosmic particles with an energy millions of times greater than the energy of protons in an accelerator have been bombarding the Earth. And this hasn't led to the appearance of black holes on the planet or other terrible consequences. It's unlikely that such an experiment inside the LHC would transport us to another dimension. But moreover, I'm carefully monitoring everything that happens with it. So if anything ever goes wrong, you'll be the first to know about it. Don't forget.
Yeah, my final thoughts. I'm very intrigued by science. I love it. Um, you know, I think as long as there's a lot of precautions taken in these types of situations and these events, um, there could be really good outcomes out of this. But you're also taking huge risks when you're doing stuff like this. So, but that's what I'm saying is the Hadron Collider has been on for quite some time, and I had a very odd experience years ago. This is back in I want to say like 2012, and I literally like lost like 5 minutes of time. Literally, 5 minutes of my life like just went missing. And like I said, if they're generating black holes, or they're tunneling into different dimensions or whatever, if that's possibly the case, then I'm sure a lot of other people, and I'm telling you this as a fact, I don't think I lost 5 minutes of time. Um, it's kind of a long story. I'm not going to get into it, but maybe for a future video. But yeah, it was right around the time that they started, they were firing up the Large Hadron Collider, and I had a very odd experience. But hey, if you enjoyed this video, enjoy my commentary on it, I really appreciate you joining me. Like I said, smash that like button, subscribe up, please. If you want to see more videos like this, subscribing will really help out my channel. And share it with friends and family. These are interesting subjects that we probably should all be sharing with one another, because they're very intriguing, and they really do have a very profound effect on our lives. So thanks for joining me, and peace.